Okay, in this lesson I'm going to do some definition dumping here real quick. I'm going to talk about stereoisomerism, stereoisomers. So I'm going to try to give you guys a picture of the hierarchy of these terms. So I'm just going to do a bunch of terms and try to explain them the best I can. So we previously encountered things called structural isomers. So remember, a structural isomer is where the actual attachment of the atoms is differently. So these are structural isomers, right? Because they actually are attached differently. There's 4 carbons in a line here, and here there's a branched carbon, right? Well, now there's another type. We did another type of structural isomer, a more specific type, which was a positional isomer. So these are positional isomers, which I want you to understand is a type of structural isomer. Right? It is a type of structural isomer. The hydroxyl group, we'd have to break the bond and remake it in order to switch between them. So when you think of the sort of the flow chart of these terms, we have isomers, then we have structural, and within structural, one of the types is positional. And there's a few other types of structural isomers, but we're going to more go over with this other side. We're going to go to something called stereoisomers, which are separate and distinct. So I'll come back, I'll redraw that in a minute when we get all the terms down. So structural isomers, or stereoisomers, I'm sorry. Stereoisomers are isomers who are connected in the same way but differ in the orientation in space. Now you might think that might be something like this, like these are structural isomers, or stereoisomers. And they're not stereoisomers because of the free rotation about the single bond, right? That's what conformation is all about. You get stereoisomerism in a couple of different ways. There's 2 things you can get. You can get the presence of a chiral center, like we saw. So no matter what I do, this and this these are not, I mean, they're the same molecule in a sense in that they have the same attachment. Both of them have a carbon with A, B, C, and D all attached, but it's the arrangement, it's the spatial orientation that makes them different. So this gives us stereoisomerism, but also we can get stereoisomerism by something we've seen before, which is structural rigidity, so either through a double bond or through a ring, right? So this is just cis-trans isomerism, and we've seen this before. So we have isomers, we have structural over here, we have stereo, and we actually have cis-trans, and then we have enantiomers. And then there's another type, actually. There's diastereomers. And under diastereomers, epimers are a type. Epimers. Epimers are a type of diastereomer. So you might want to bookmark this, you might want to look at this and come back and check this out after I'm all done describing what these terms are. Enantiomers are stereoisomers whose images are non-superimposable. So this is something that is chiral, and it's mirror image, right? So these are non-superimposable. They are called enantiomers. The two-handednesses are your 2 hands are enantiomers of each other. They are non-superimposable mirror images. Diastereomers are molecules who are not mirror images of each other. And in fact, I probably drew my chart wrong. I'm going to have to go back and fix that. Cis-trans isomerism is a type of diastereomers, so I should have put cis-trans under that, but I'm not going to worry about that too much. Epimers, I will have to actually get to another lesson, I realize. So epimers are actually a specific kind of diastereomer, and I'll talk about that when I talk about Fisher projections and when I talk about